So yeah, we started the Bernoulli equation, Bernoulli theorem. So we had three terms: static pressure, kinetic pressure, and the third term is due to some reference and position of the streamline with respect to reference. We call it hydrostatic pressure. And I told that these two values, whether we call stagnation pressure so the pressure that we understand is this one. And generally, to measure the pressure, we use some sort of capillary to check how much water is rising and all. And that will help us in determining the pressure value. This is called dynamic or kinetic pressure, which is always created at the expense of loss in the first value or maybe second value. And that sum of these three terms along a streamline is always constant quantity. So the sum of these three is always a constant quantity. This is what we need to remember. So we have seen the venturimeter in case of liquid flow. So similarly, we have venturimeter in case of gas flow. So in case of gas, the same design will not help. The reason is obvious. So let's say if a gas pipeline is there, and if you insert this tube, gas cannot rise up, right? It's not like the liquid you can see the pressure by rising the height. So we need to change the design of the venturimeter in case of gas flow calculation, and design is pretty much simple with just one difference. So come to now. So we do not put a tube above as in the case of liquid ventilator. So let's say it's a CNG pipeline or LPG pipeline. So you might be getting CNG in your car or maybe LPG at home. But these pipelines are traveling across borders also, and these are very much physical pipelines. So so now as the gas will move through the across the tube, so if I name it 1 and 2, so at which location the gas will move faster? 1 or 2? Tell me, guys. So the flow rate will be bigger at 1 or 2. Am I audible, guys?
1.
Yeah, so you can reply. At which location the flow velocity is bigger?
1.
So what we do next is, this is a complete shape. In the bottom U tube, we put some liquid. So because pressure, okay, now velocity is bigger at 2, so at which point the vacuum will be created more, 1 or 2? If you move very fast, then at this point the pressure will drop, and therefore if you put some liquid inside the tube, then because of the vacuum, it will be sucked up. So liquid level will rise in the right column. Why? Because the pressure is less. It is like a vacuum creation, because the faster the gas will move, it will not press this side. Understand? So here the pressure at this location, if I say P1, and pressure at this location if I say P2, and the density of air or gas we call rho G. But here we have liquid, so we have a rho L value. So this difference of pressure and this height difference, you can always relate. So if you want to relate exactly, you can say that this is H1, this is H2, full value. And you know how to write the dive in, dive out property in a tube. So you're entering at one pressure, but you're exiting at some different pressure. So by diving in and diving out, we can relate the two, which is pretty easy. So we can P1 plus rho G H1 minus rho G H2 equals to P2. And we have also realized that P1 is bigger than P2. So you can see the difference of pressure is automatically H2 minus H1, and therefore this is equal to rho GH. So the whole purpose of tube, the fitment of the tube in this venturi meter, is to calculate the pressure difference at the two cross section where the tube is fitted. So the entry of the tube is at a different cross section and the exit of the tube is at a different cross section. So it means it will encounter the two different pressure, and as a result, the liquid will rise or fall in one of the columns. You can see where the pressure is high, the column length is small. Where the pressure is low, the column length is bigger, because it is like a vacuum pump. You suck the air, and therefore you create a partial vacuum, and therefore this partial vacuum will, kind of pull the water or liquid up, or any liquid. This is generally mercury we use, not water. So can you guys do the rest of the analysis, like apply the Bernoulli equation at the two, write the continuity equation, and tell me the V1 V2 value, or tell me the discharge value. I want the value of Q. And you can assume the cross section here as A, and okay, A1, and here as A. So how many steps? Step 1, equation of continuity. Step 2, Bernoulli theorem. Step 3, ratio relation. Okay, that we have already derived actually. Step 4, solve. So you guys should try at least once, then I'll give the solution. Okay, go ahead and solve this. And if no one is interested in solving, then just let me know. I'll solve. Not an issue. Done. So anyone solving this question, please let me know.
Yes, sir. Sir, can you solve this one?
Okay. So okay. So now the simple EOC is what? A1 V1 equals to A2 V2. You have to assume velocity V1 V2. Hmm? So let's say at this cross section velocity is V1 here A2 V2. Apply the Bernoulli equation. What we should write? So we can choose a streamline, horizontal streamline, right? And if I choose this as a reference, then the third term will not appear, which is good for us. So let's write the answer. So the pressure is static pressure plus kinetic pressure. And you can also write here is static plus kinetic. See, you have to just remember the Bernoulli theorem, like the three terms you have to learn to write three terms. That's it. And rest you can discuss how to write and not. Okay. And also remember that whenever we connect some kind of tube, the only purpose of tube is to know the difference of pressure. So you can enter the tube and exit the tube and you can find the pressure difference. And step 3 is pressure relation that we have derived. P1 minus P2 is rho GH. H is the difference. So can you guys solve this question? Yes or no? If you still can't solve, then okay, I think I cannot help much. So you can substitute the difference of here from here, and then from A1 B1 to A2, you can find velocity, and you should get the answer. Okay. So the difference of pressure is basically equals to half rho. This is the pressure difference, is rho liquid. This is the rho gas, and V2 is coming V1. So unlike the previous cases, the rho term used to get cancelled. Here it will not happen. So the relationship will change. So it is rho L by rho G into 2GH. And from the continuity, we know V1 is A2 V2 upon A1. So rho liquid by rho gas. So we are writing Bernoulli equation for gas or liquid. Tell me. Okay, you guys will not tell me. So V2 square turns out to be so we got V2 equals to under root of rho liquid by rho gas into 2GH upon 1 minus A2. And the discharge flow rate will be A2 V2. So you can add A2 under. See, these are things which you need to practice, because it's like until you will not solve one or two questions on your own, the flow will never come. So that's why I'm like kind of forcing you guys to solve right now, but you're not getting it. I mean, you're not getting my intention. So that's anyway. So I know where you can get stuck. See, things are these are simple chapters, but still most students don't find it easy. The reason is they just don't get into it. That's the problem. If I'm saying you solve it, then you have to force yourself to solve this question. And if you're not solving it, it means you're not learning anything. So that's the problem with the fluid mechanics. We are going to forget everything very soon. The moment, I mean, I think I will go to next chapter, you will be completely forgetting this chapter thoroughly. With no idea what to do. Okay, so let's do the airplane problem. The airfoil. So in case of airfoil problem, what we are going to consider as this is the cross-sectional view of the plane wing. So this is the cross-sectional view of the wing of the plane. Okay. So streamlines are going to be pretty much simple. So below it will be like kind of almost undisturbed, and the above the streamlines will be leaving the surface and then bending like this. So generally plane do not fly like this, so they always keep the wing. The reality is like they keep the wing like this, and this is called angle of attack. So they hit the air at some angle to generate extra lift. So if you keep it exactly flat, then the attack will not be there. So this they keep it at maybe 10 degree or 12 degree, 15 degree at max, and this is called angle of attack. So anyway, that's not of interest. So to make it simple, I mean just to understand the lift condition. So we have full-fledged plane. What you're looking at is the cross section, and if the plane is moving with velocity Vp, then in the frame of the plane, let's say plane is a frame, the layer of air below will move together and it will move. So generally, uh, the two layers will move differently. So let's say this air is moving with velocity v, and this layer is moving with velocity v. We can assume like this, not an issue. So the air velocity above and below will be different. Generally, v1 is going to be much bigger than v2. Yeah, on a relative context. And the difference of the, I mean, of course, the v1 v2 velocity, generally we take v2 as 0 and we take v1 as same as plane velocity. So either you can think of plane moving through the air, or you can keep the plane fixed and air is moving across the plane. That's the same thing in a relative plane. So because the Vp is there above and below is nothing, so the pressure below is going to be very high than the pressure above. And this gap is the vertical height is almost negligible, so we can ignore the third term again if you remember by considering this as a reference, and the size of the wing is not much, so we can write that P1 plus half rho V2 square P1 P2 plus half rho V, just mismatched the notation. I should have this is this. So P2 plus half rho V2 square equals to P1 plus half rho V1 square. So, so now this is pretty easy to understand that the lift that we generate is because of the difference of pressure only. So we can say P2 minus P1, which is the pressure difference, is equal to half rho air and so generally the difference of pressure, that's called delta P, and the velocity difference is we take one velocity as almost zero, so this is as good as Vp square, and therefore you can see that there is a relationship between the plane velocity uh, and the delta P. So P Vp is 2 delta P. So if you try to move really very fast, then the maximum delta P is how much? What is the maximum possible value of delta P? So maximum means the above is vacuum, below is atmospheric. So the maximum is PAT. So we cannot generate a difference of pressure more than this. So you can remove completely air from one side and you can assume air is only on the other side. And because we know the atmosphere can exert only PATM, so the maximum difference we can create is PATM itself, not more than that. And therefore, there is no benefit of moving faster than certain values. So the maximum velocity for maximum lift. So velocity corresponding to the maximum lift is 2 PATM. And this will give you some basic idea of how fast the plane can or should fly to create the maximum lift. And this puts the upper limitation that what is the highest plane speed that we should achieve while manufacturing. This is 2 into 10 power, let's say 5 upon density of air is 1. So this is 20 root. 20 is 2 root 5 kind of meter per second. So you can imagine this is a 2 into 2.235 out of 6. This is a 4.46, or you can just add 4.5 into 10 power 2 meter per second, which is how much? 450 meter per second. So in terms of kilometer, it will be how much? You can guess easily. So 450 into 18 by 5. Roughly it's giving you the very idealistic value of 1620 kilometer per hour. But generally we do not achieve this. So the maximum speed achieved by planes are like around 1000 to 1400 kilometer per hour. Maybe in the recent times some development might be there. Let me check what maximum light is. Oh, that's too much. No, these are supersonic uh, passenger airplanes. Oh, good. This is supersonic. The Airbus is like 676 miles per hour. Boeing is 652 miles per hour. That's meaningful. Around 1,000 km per hour. So supersonics do not follow the just lift condition. They do have the exhaust propulsion, and due to which they achieve extraordinary velocity. Anyway, so this is the airfoil problem, and you should know. So the next problem is again a very famous problem. Tap problem. So so in case of tap problem, imagine this is the opening of the tap, and as the liquid will rise, sorry, it will fall. The cross section becomes narrower as it goes. So as long as it is streamlined, we can do some calculation. So let's say this cross section is having radius R2, R1, and this is the height is. So I just want to know the velocity relation of this cross section. V, V, yes. Or I could say R1. Anyway, so it's pretty easy to find because this is a tap problem, and the Bernoulli equation we are trying to write at two cross section at different level. So if I choose the final as the reference, then we can write the third term as well, right? Or you can choose anywhere. Doesn't. So I'm taking the final cross section as the reference, or the bottom cross section as the reference. Now, what we need to realize that this entire liquid is open to atmosphere, so the pressure at every cross section will be same. So if I say the pressure here, it's P atmosphere. If I say pressure here, it's P atmosphere. So you can choose anywhere and you will get the same pressure, P atmosphere. Hello, hello, hello. 1, 2, 3, 1, 2, 3.
Yeah, sir. Now you're audible.
Okay. So V1 square is equals to, we can write in terms of radius. So V1 turns out to be under root of Gh upon and now because we have got all the answers, so what we can do next is we can find the discharge rate. So at what rate the tap is releasing the water, you can write as pi R1 square V1. That's it. So knowing the cross-sectional radius of two different level, we can relate the terms like this. So that's a tap problem. So what we have seen is the vertical, when things are moving vertically, when the levels are changing, then the third term will appear, and this is the example of how to use the third term. So any vertical flow will demand the third term. Okay. So next we can go to something called Retorts Tube. But that's simple, just like time pass. So okay, I will not solve this question. I mean that's so easy. You can just search about Retorts Tube, read from Wikipedia, and when you solve the sheet or Erodov. Okay, for this chapter, Erodov is highly recommended. So you are supposed to solve Erodov completely and like from beginning to till the end. Okay. So highly recommended. In H.C. Verma, questions of dynamics are very simple. I mean, that's not up to the level of J. So solve from the Erodov. All questions, every question. Then you can ask doubt of question, tutorial class or okay. Next is of interest. Yeah. So which other tube is left? Okay, I think that is sufficient. So there are some examples which I'm leaving. So now we can go to the next concept called Torricelli theorem. So in maybe in chemistry, you might have came across the unit of pressure torr. So I think
Yes.
that is in the honor of like physicist Torricelli. I don't remember the full name. I think Daniel Torricelli or something. Torricelli full name. Yeah, Evangelista Torricelli. Yeah. Yeah. Now, so he was an Italian physicist. Nice. So knowing history is really interesting. Okay. So what is told is very term? That's interesting. So he said something like how the liquid will move through a hole which is really small called orifice. If we have a container, this container is open to the top, and if you pour some liquid, and let's say if you make a hole at the bottom, so liquid will fall. So the whole idea is liquid will come out at some speed. Let's call it V. And the question is at what speed it will come out. So what Torricelli said that velocity of efflux, or simply velocity. So velocity of liquid, wait. So velocity of liquid coming out of orifice. The velocity of liquid coming out of orifice is when orifice only depends on height of the liquid above the orifice. So what I mean by orifice? A very tiny hole. So let's say if you have a packet of milk and if you just puncture it using a prick it using a needle, then that kind of leakage we can say orifice leakage. So what producer is saying that the velocity of the efflux coming out of the orifice is only depending on the what is the height of the liquid above the orifice, like this height. So it means if I prick somewhere here, then what will matter? This height. If I prick somewhere here, then what will matter? The height from here to here. Okay. So the velocity only depends on the height of the liquid above the orifice. Do you realize what I'm saying? Okay. So again, we can find using the Bernoulli equation. But in this case, the area will not be given to us for the obvious reason. So orifice means a very small area. So if I take the big area as A, and the small area is small a, then the orifice refers to the relation that A is very, very smaller than capital A, maybe 100 times. So if that is the relation, then A by A ratio will tends to 0, right? So you can say A by A is, or you cannot like this. A by A will be much smaller than 1, right? So even if we try to write the equation of continuity, you can see that the velocity capital V will follow this relation, and because A by A, or you can say V by V is A by A, which is very, very smaller than A, 1. So capital V will be very, very small compared to. So these are the approximation that we have to follow. Understood what I'm saying?
Yes.
So that is the meaning of orifice. So when we have a problem with orifice, the velocity near the big cross section is totally ignored. So we assume almost stationary or static while applying the Bernoulli equation. So this V, capital V, you can assume, but of no use. So now you can write the Bernoulli theorem between this cross section and just outside the container. So you may be wondering why this cross section. If I choose the cross section 1, we know the pressure here is P atmospheric, right? And the pressure just outside the container, which is this is open to air, this is also P atmospheric. So that's the beauty. The the first term will be same, and therefore it will get cancelled out. So how to write the Bernoulli theorem between 1 and 2? I will tell you, you can choose any two cross section, not necessarily 1 and 2, but that's easy. So at 1 we can write P ATM as the static pressure, and you can write the kinetic pressure is half rho capital V square. And again, it's a vertical motion, so we can choose some reference here. So the third term will appear as rho G capital H. Now coming at the 2, the pressure will drop to PAT. The kinetic energy becomes half rho V square. And third term is 0 because that's I have taken the reference. And this is tending to 0, it's very small. So that's why you can see it's a simple answer. It is like a free fall kinematics formula under root 2. So that is the whole idea of Torricelli, that in under these approximation, the velocity will depend only on the height of the liquid above the orifice, nothing else. So you can always derive the formula like this, and we can ignore the capital V in comparison with the small v. So I am just making 0 there only. If you do not want to make 0 there, you can bring it here, solve it, and then probably you get an answer as 2gh upon 1 minus a by a the whole square. But you know that a by a is so small compared to 1 that this is as good as 0. So 1 minus 0 is 1. And therefore this is 2gh. Understood? This is using the previously derived formula. Okay. So if you want, you can do this if you are getting confused. So is this clear, guys? What is happening here?
Yes.
Okay, so that is a Torricelli theorem, but you can write in other ways also. So let's say I bring a third point, I mean the point 3, which is just inside the orifice, and 2 is just outside. So how the Bernoulli theorem will appear? So BT, if I try to write 3 and 2, the good thing about 3 and 2 is the third term will not appear. Why? Because they are almost at the same level, right? So what is the first term? Pressure inside the container. PATM plus rho G capital H. This is the P, the P of Bernoulli equation. This is the P of Bernoulli. Okay, do you realize this? P means what? The net static pressure we have to write. And the net static pressure is the sum of atmospheric and liquid column. If is this clear? The second term
Yes.
is half rho capital V square because it's a big cross section. And the next is EATM because that's only static pressure. I'm putting in parentheses so that you can understand this is the static part. Okay. and the velocity is half rho v square, and the third term is of course not there. And you can see the way you think will not affect the answer. So when I'm putting in the bracket, it means it is the net static term. Okay. So the rest is same solution. So this is also tending to zero. So when two cross sections vary too much, then we can just ignore the velocity of the big cross section. Now, in case if you wish to know the discharge rate at this instant, then the size of the orifice area into velocity. That is what we do generally. Now, this is the answer at the instant when the liquid level is capital H. Now, what happens if the liquid level will keep on changing? The next question is very interesting and very famous. So, the question is calculating the time. So, calculating the time to emptying the vessel. To emptying the vessel. Yeah. So, we can take the same example. Sorry. Am I audible, guys?
Yes.
So, let's say you begin with capital H. So, of course, as the time will progress, the level will decrease. So, let's say at some random instant t, the height is still left okay, small h. And now, of course, let's say this velocity. Okay. So now this is t equals to 0. This is t equals to t. And I want to know that when this will be completely empty once you open it. So we can assume the cross section area is capital A and small a. So this area is capital A, and this area is very small. Is small a, and this condition is satisfied that A by A is, so orifice condition is satisfied because we want to find the Torricelli theorem. So what we can write about V? So here the V must be equal to under root 2gh without solving. No need to solve. You can just apply the Bernoulli theorem and you can say this with full confidence that whenever the orifice condition is satisfied, we can write V equals to under root 2g, the height of the liquid above the orifice. That's the rule. So imagine I can create a vessel like this, and I put the water. This is L. This is L. And if I create the hole here, huh? if this is orifice, then what you expect the velocity here? V equals to under root 2g h. But what is h here? If it is symmetrical, okay, this is okay. I should mention this also. If it is symmetrical, then I can find this height, right? And this will be exactly how much? L by root.
L by root.
And therefore the velocity connected is under root 2g L by root 2, which is like root 2g. So the whole idea is that torricellism is so useful that once you know the formula, for rest of the scenario, just check. You have to check the height of the liquid above the orifice. Nothing, no need to write the Bernoulli equation. So this is like pretty much straightforward application of Bernoulli. I mean, of course, we derive it from Bernoulli, but once you derive it, you do not, you no longer need the same. So you can just use the formula and just solve the question. The only rule is the orifice condition must be satisfied. The two cross section must vary significantly. Okay. So now, as the water will come out, what is the discharge at what rate the liquid is leaving the vessel? It's pretty easy to write. A under root. Okay. So imagine after some time t dt, the liquid layer will reach here. So let's say this is at t equals to t, and but that very next time t plus dt. So after time dt plus dt, this will decrease. So if the height was initially h, now what we can assume? Let's say this new height is what we can see.
H plus DH.
So what is this height? How much water has left?
DH.
No, this is minus
Minus
DH.
DH. Minus.
So the amount of liquid that has left in time dt is how much? So you can find the volume. So d volume is cross sectional area into height, right? This is the water that has left, isn't it? So the rate will be how much? D volume by dt is how much? Minus a dh by dt. So you can see that the discharge we can calculate in two ways. One as a big cross section, which is a dh by dt, and one other is a small cross section, which is a and Torricelli theorem, the AV. But the rate at which the water is diminishing is the rate at which the water is leaving the vessel, and therefore these two values must be same, isn't it? So do you guys realize this? This is very important.
Yes, sir.
So the next step is pretty straight. So the equation is pretty simple. Minus a dh by dt. Well, why dh by dt is negative? Because definitely it is slowing down. So minus means dh by dt is negative, so minus will make it positive. So we are writing the value a under root 2gh. This equation is continuity equation, nothing else. You can write a1 b equals to a2b. And we are writing v equals to minus dh by dt for the obvious reason. So you can think the way you want. I mean, up to you. But once we have the equation of continuity, our job is pretty much straightforward. So dh upon root h is a by a 2g, because this is constant, into d. And now we are into the condition of integrating. So what we can write here is that when time is 0, the height of the liquid in the vessel was capital H, and when time is t, it is small h, and you know how to integrate. And if you don't know, okay, I can tell you the answer. This is 2 root h. Right? This is 2 root h integration. I think so. This is from capital H. Oh, so the time t turns out to be a by a under root 2g 2 under root capital H minus small h. Right? This is the nice answer. So this is under root 2 by g, right? Oh. So now t equals to a by a, and if you multiply, it's very interesting. I think this should be interesting. Hmm. So this is like a formula of free fall. If you remember the free fall of the liquid 2h by g, okay. So we have the answer a by a, 2 capital H by g minus 2h by g. So when you make small h equals to 0, you can get the full time. So time to empty the vessel. When small h equals to 0, you can just check it out. I mean, if I am made some mistake, but this should be the right answer. The total time period to empty the vessel is a by a into, and this is quite meaningful because we know this answer 2h by g. It's a very famous answer from kinematics. So imagine if you have a vessel and the bottom, you remove the bottom completely. So all of the liquid will free fall. So after what time it will empty? So when it will travel h height below. So the answer is 2h by g. We know this answer. But because of the cross-sectional ratio, this will take a lot more time. So A is big, small is small. So this ratio is much bigger than 1. So this will take a lot of time. Is this clear, guys?
Yes.
No, this derivation is very important because generally we can create a question of sound in using this container problem. So what we do is, if we study later on that we place a tuning fork which oscillates, and because of the oscillation it creates the wave compression and reflection, and it creates the standing wave in the cavity of the vessel. So what happens that as the time will progress, height will change. So at some time you will listen to the resonance or some whistle sound. So we will be doing those things in the chapter of wave and sound. But this formula is very important because this is the JE advanced question of subjective nature long time back. So this formula is this derivation is crucial, but not difficult. You can of course always do. So there are some very standard problem that one should know, or the range problem. I mean, these are very subtle, famous problems that one should just by heart. So we have a vessel which is open from outside, top, and it is filled with a liquid completely. And this height is, let's call it capital H. This is the bottom. And you will see these questions in almost every book. Almost. Yeah. So the whole idea is if you drill the vessel or punch the vessel at a height small h from the bottom, and if you do the same from small h from the top, so if you puncture a hole at these two locations, So which velocity will be bigger, v1 or v2? Let's say this velocity is v1. This is v2. So which will move faster, the top or the bottom?
Bottom.
So as per the Torricelli theorem, the velocity of efflux will be depending on the height of the liquid above the orifice. So v1 is how much? What is v1?
Root 2G.
And what is v2?
Root 2G H capital H minus 1.
Okay. So now, because you know the velocity and it is just like a horizontal projectile motion. So what do we expect that the range? So not to your surprise, if the top will fall here, the bottom will also fall here. So they will have same range. That's a interesting point that you need to remember, and that's very easy to prove. So what is the formula of range? V1 into time of flight. So 2gh, and the time of flight for the horizontal projectile is 2h by g, which is 2h minus h by g, right? Because you are at a height of h minus h from the bottom, so you will take this much time. And if you try to find the range of the 2, which is v2 into t2, so v2 itself is 2gh minus h, and t2 is how much? 2h by g. But if you multiply both, you can see the answers are same, right? So the answer is 2 under root of small h into capital H minus h. And this is the same here. So that is why the R02 will be same. So if you drill a hole from bottom and top at the equal height, then the liquid will traverse the same distance. And because it's a kind of quadratic equation, if you see inside the root, so it will have some maxima and minima. So where we must punch the hole to maximize the range? So that's common sense. Huh? You can say common sense. It must be center. Right? So center will have the maximum range. So now you know that, I mean, if you want to see, of course, if your intention is to maximize the range, you know where to, make the hole in the tank. Okay, understood? And the maximum range is how much? This will be 2h. No, sorry, h1. Because it is h by 2, h by 2, h by 4, yeah, h. So if I maintain the liquid level always h by attaching a tap here, so this tap will always keep this vessel filled, and the maximum range cannot exceed the height. So now these are like something very much ready to answer problems. Like you should know the answer in advance and just mark it and come back to after examination. So rest you need to practice, but these are very famous and very typical problem, I would say. In examinations like BitSat or JE mains, I mean, knowing this will help. You can directly answer the question and save your time. So these are ready-made answers. Okay. So what else is left? Is there anything left? Mm, Yeah. So yeah, one thing is left. You can think this as a multiple liquid chrono. Slightly advanced. This is the slightly advanced concept, multiple liquid chrono. So we are all still doing the Torricelli. But what if we have a non-immiscible liquids? Now, what is it? So let's say you fill the bottom with some liquid, and then you fill another liquid. So let's say we have two liquids of density rho. And if you make a hole of puncture at the bottom, so we are doing it some in general time. So the liquid will come like this. Yeah. Um, not this. So what you can see that in the very beginning, the liquid number two will start leaking out of the vessel, and once it will be emptied completely, then the first will start leaking. So when both are present, okay. So let's say after some time, the situation is like this. So the situation is like this. The liquid has reduced. The first liquid has reduced. The second is completely intact. So this side is small h. This is h1. Okay. So now, what is the let's say I want to know the velocity of the liquid coming out of this instant at some random instant. I want to know the velocity right now. So, so I can apply the Bernoulli equation for the sake of simplicity between one and two. And see, that's very interesting that when the liquid crosses the boundary of a vessel, that is sufficient to accelerate them to any velocity. Now that's very interesting because every vessel, which is a physical vessel, will have some thickness, and that is sufficient to accelerate. Okay. So the pressure is so powerful that even if you move a tiny bit, your velocity will be significantly increased or decreased at the same time. So one and two. So if you write the Bernoulli equation between one and two, we have to write the pressure difference only because the third term is anyway not there. So the pressure at one is much bigger than pressure at two, and this much equals to half rho V square. I'm just writing quickly. I'm not writing the entire thing. And the difference of pressure is pretty easy to write now, because this is the top pressure plus the bottom pressure. Oh, I need to mention the density also. So rho 1 GH1, rho 2 GH, and P18 will cancel out. So I'm not writing it. So this is half rho. The liquid which is coming out is 2. So half rho 2 V square. So you can see that V turns out to be 2 GH plus rho 1 H1 by rho 2 into G. Yeah. Yes. So I think the answer is simple. Yeah. So V turns out to be how much? Under root of 2G H plus some constant. And what you can realize that when the liquid 2 is leaving it, then this is the relation. Once the liquid will be emptied, so now for finding the time period, we have to just do the. So how much time it will take to empty the liquid number 2? So you can write minus a dH by dt, the typical way of doing a into 2g with some slight, I mean h plus some constant is there. So this entire term will behave as constant till the liquid is coming out. And if you solve this, you will get the time taken to just remove the liquid number 2. Okay. Do you guys realize this? It's purely mathematical.
Yes, Anish.
And then once this will be removed, again it will go back to the only one liquid, and we know the answer for the single liquid time. So for liquid, only single liquid, we know the time will be how much? A by A under root 2H by G. That's easy to remember. So once the green liquid is emptied, oh, let me do this. I think you guys are not comfortable. So you guys have not studied the integration so far. Is it still left?
So no, it's
Hmm?
basic integration. Basic integration.
So is this beyond the basic? So if you know the basic integration, then you should be able to solve this question. If you don't know basic, then it's. So this is the time taken to empty the second liquid. So let's putting time t2. Let's put that. And then limit I will take from h2 to 0, because the variable is small h will only go from h2 to 0. So in the very beginning it was h2, now it is 0. So this is 0. So what is the integration of this? 2 root h, right? Like you can leave the constant and so I have seen most of the times students who though love mathematics, but they fail to do any single mathematical calculation in physics. So I don't know how you guys learn mathematics. That's really big concern for me. So you must be solving the question of integration, but you don't know integration. You just know some formula and some pattern. You recognize and solve it. Was anyone knowing the basic of integration could have solved this question? Nevertheless, try to learn maths. Right? So it is like root 2g is common, so I can check as well. Let me root 2g and it's like h plus some constant. You can just think of a simple some constant. So this is rho 1 h1 by rho. So what you have failed to do is recognizing the variables constant and then how to do the sum. Okay. Minus no. So T2 turns out to be minus a by a, and this is root 2g also, and this will be 2 root h. So mm, minus 1 h2 plus root 1 h1 by. Hmm, this is nice. So T2 is how much? A by a root 2g and 2 outside. So what we get is rho 1 h1 rho 2 h2 upon rho 2 minus rho 1 h1 by rho 2 and okay. So this looks very pretty easy. You can make it 2 by g and what we are left with is this is root 2. I can make it remove them from here. Okay, so the answer turns out to be rho 1 h1 plus rho 2 h2. Fine, so we got this answer, and then for total time, so T equals to T2 plus A by A, and for single liquid, the answer is fixed. 2H by G. Okay,
Yes.
so you can do it for the 3 liquids or 4 liquid or 5 liquid. So let's say, so if you do for more liquids, you can find the pattern actually. So you will also realize, okay, this is some pattern which I can remember, which of course you may not do, but yes. Let's say this is the first liquid. They will use all the colors. Second liquid, third liquid, fourth, fifth, sixth. I don't do space. So imagine we have so many liquids. Row 1, row 2, row 3, row 5, row 6. H1, H2, H3, H4, H5. Now, what you need to realize that this entire term is only contributing to the extra pressure for the liquid one to release from the hole. Do you realize this? So the role of the
Certainly.
the role of the liquid above the first liquid which is coming out of this hole. See, through the hole, what is coming? Only one liquid, right?
Yes.
So let's say if I'm only looking for velocity of the first liquid, so what is the other liquid doing here? They are only creating the pressure, right?
Yes.
Earlier the pressure here and here used to be same. Now you can see the pressure here is different. So how much pressure will differ? It will differ by the liquid pressure of all these liquids, right? Can you realize this?
Yes.
So if I write the Bernoulli here and here, then my job is done. So P1 minus P2, because I know that the loss of static pressure from 1 to 2 will give the half rho1 V1 square. Let's go. That's pretty easy. And the P1 is how much? So pressure at the topmost layer of the first liquid is very simple to calculate. It's PATM plus all rho1, H1, rho2, H2, rho3, H3, and so on. So to generalize this, can I write summation of rho I HI into G, because that's the format. This is the first pressure, P1. And P2 is open to atmosphere, so this is PATM. That's it. Okay. One more thing I'm missing. Okay. The third term will come here because we're writing between the two different levels. So why don't we write this at exactly here? If I make one here, then things will be much better. But yeah, that's okay. I can remove the one from here and let's see. Okay. Diagram will be disturbed, so I have to remove. Yeah, now this is. So if you write the Bernoulli equation here and just outside, that's easy for you. Choose one here, two. So at one, the net pressure is how much? PATM plus summation of rho I HI from I equals to 1 to whatever n whole into G minus PATM, that's the outside, and this is equals to half rho 1 V1 square. Okay, so the answer is pretty much simple. So the V1 is square, V1 is simply 2 G, and you can say H effective. So what is the H effective? Can you calculate the H effective? Yeah. That's a very interesting calculation. So H effective is how much? Summation of rho I HI, I equals to 1 to all value upon rho 1. This is called H effective. If the liquid 1 is coming out, then H effective will be divided by rho 1. If the 2 will come, then whatever is left that time upon rho 2, then 3, then 4, then so on. So you can always calculate the H effective separately and do the calculation. That will be easy for you. So instead of doing all calculation, just find the H effective and uh, yeah. So I can also write, because this is uh, 1. I can write as rho 1 H1 plus, then I can just wrap up the rest value I equals to 2 to n upon rho 1. So this looks H1 plus summation of rho I HI, which is, does not keep H1 upon rho 1. So this will look like this. Up to you the way you want to solve, uh, but this is pretty easy. what variety I'm using. So there are many variety of questions which I have left intentionally so that when you solve and when you get doubt, you can ask me. At least you will have some fun left. Yes, I will take away all the fun while solving the question. So I think the last concept is called. Just let me check if I have some conceptual question. Then yeah. Mm, yeah, rest are like pretty much straightforward question which you know already. So the last concept which I left, I told you that I will be solving this in the chapter of fluid called the Reynolds number. Or did I solve this Reynolds number? Done? Yeah, this is left. So we have seen that the Bernoulli equation is only applicable for the case of streamline flow or the laminar flow. So Reynolds number is the some sort of metric which suggests that whether the moving liquid will follow the laminar or will follow the turbulent flow. So generally, I mean, let me give you the exact value because this is something controversial going on since ages. So we really do not know what value JE consider as uh, laminar and also. Okay, so this is 2000. They're taking that's good. Okay, so there has been quite a lot controversy that what value should be taken, uh, and everyone is like taking a different thing. So if the Reynolds number, if we will learn how to compute, so Reynolds number is basically uh, proportional to the ratio of so it is the ratio of like a thrust force upon viscous force. Now thrust force means so when we have a tube, so we'll only consider for the cylindrical tube. Our syllabus is only meant for the cylindrical tube. Of diameter d. So the liquid will flow because of the pressure difference. Like the thrust is the force which propels the liquid, and viscous is the force which opposes the flow of the. The thrust will push and viscous will oppose. You can think this way. So if the viscous force is very high, it means you cannot move very fast, and therefore the flow is bound to be streamline or turbulent. What do you expect? So if something is moving really slow, when you open the tap which moves the water really slow, what you see? The laminar flow or the turbulent flow? The known is there. Huh? Am I audible?
Yes. Sir, can you repeat the question?
Question is simple. I mean, if the viscosity is very high compared to the thrust, the flow will look like laminar or turbulent, random or
Laminar.
some. Hmm? What did you say?
Laminar.
Laminar. Yeah,
Yes.
that's correct. Yeah, laminar is the right word. And that's very common experience that if we have a motion is very slow, if you open a tap really slow, you can see it's a laminar flow. But after that, it becomes turbulent. So we can empirically derive the formula of Reynolds number that, and we will be deriving only for the tube, which is cylindrical in shape. So the thrust force we write as a density into area. Area is like this. Rho A V square, something like this. And the viscous force, we can use the some formula because we just want empirical relation. So we can use the Stokes law. If you remember 6 pi eta RV, so we can add eta R as something subdimensionally. I'm just thinking. The whole idea is, I mean, of course, this is not a derivation at all. The whole idea is we can choose some formula for viscosity, some formula for the thrust, and we can just substitute. And this will give you the empirical relationship. So one D will cancel out, one V will cancel out, and every constant we can ignore. So what we left with is density, diameter, velocity. I'm ignoring all the constants, and what we left with below is only eta. So this is the way to derive it. So Reynolds number is actually written as the same thing. Rho VD. Okay, I will not like this to read clearly. Rho VD by eta. And this is the definition like kind of adopted by the physicist or mathematician. Okay. So D is the diameter. You can also write as rho V 2 rho V radius upon eta. So if the Reynolds number is turning out to be less than 2000, flow will be laminar. And laminar flow is such a flow that when you look at the laminar flow, it looks like there is no movement at all. So you won't be able to see the movement. And I have some pictures which I have clicked in my washroom, laminar flow pictures. Yeah. So hopefully, if I find today, I'll show you. It looks like there is no flow happening at all. I'm not sure if I can find, but oh, okay, I'm not. Okay, for me it's difficult to find. Sorry, okay, I don't have. Anyway, so this is what you are supposed to remember the formula, and there are few questions which are based on which are given in the Erodub to solve this problem. If the Reynolds number is between 2000 we call it transient state. So we are not sure what is going to happen. So it could be laminar, it could be turbulent, but we cannot, say anything. That's the point. And if it is more than 3000, then we say surely it's a turbulent. Okay. So this is the empirically derived formula. I mean, there is no formula like this in book. You have to just mug up. But I just found a way to actually coming to the formula through some manipulation. So this is the manipulation, not a derivation. So manipulation, not okay. So what is that? I think, we are done with everything. So I can suggest some reading. So you can go to the website, the Hyperphysics, and you can search about the fluid mechanics. So they mention a lot of informative thing, which is really sorry useful. Okay. So we have done the Coaxial equation in the viscosity chapter itself. So that's done. All right. So I wish you all guys a very happy Holi. So celebrate with joy, have masti, and we'll meet after the not Holi. I mean, probably I will keep class on Monday itself or Tuesday max. Then this month I will not keep any lecture because of some examination I have to do, and then I'll start from the April. So you will have maximum one or two lectures this month. Then I shall start from the April 1st. All right. Happy Holi.